Hi everyone. So in this video, we're going to be putting together some of the concepts from the last couple of videos. So things like end behavior, zeros, and multiplicity of zeros. And we're going to be seeing how those different concepts come together to shape the graphs of polynomials. One thing I just want to mention before I get started, as I was editing my last video, I noticed that the microphone quality seems to have gone down a little bit. I really don't know why that happened. I bought the microphone that I'm using at the beginning of COVID, and I've been using the same one all along, and I don't know why it suddenly sounds worse. So I apologize for that. Hopefully it's, you're still able to understand me okay, and it doesn't sound too bad. Okay, so I want to start by just reviewing a couple of things from last time, just so we have them kind of all written down in one place. So the first concept that we learned about in the last video was a zero. So we learned that a number c is called a zero of a polynomial f of x if f of c is equal to 0, right? So if when you plug that number in to the polynomial, you get 0 as your output. And one thing that we also mentioned that will be useful in terms of graphing, which is what we'll be doing in this video, is that when c is a 0, then we know that the point c0 is an x-intercept. And then the other thing that we talked about in the last video is this idea of multiplicity. So we said that a 0c has multiplicity m if the factor x minus c, so another thing we talked about is that anytime you have a certain 0, you also have this corresponding factor. So if that factor appears m times in the factorization, that number m tells you the multiplicity of that 0. So the main question that I want to address that will be kind of our first new material of the day is how does the multiplicity of a 0 affect the graph? What does multiplicity tell us about how the graph of a polynomial looks? So we're going to be coming back to this picture in a little bit, but I just want to point out a couple of things here. Notice that if we look at this graph, we can see that there are a bunch of x-intercepts, right? We can see that the graph crosses the x-axis here, 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 here. And actually, I shouldn't have said cross, right? Because in some of those places, the graph goes through, right? This first part, the graph is going through. So at that first point, the graph is crossing the x-axis. But at these next 2 points, notice that the graph actually doesn't pass through the x-axis. It just kind of touches it and bounces off. But no matter what, it doesn't matter whether the graph passes through or touches the x-axis and bounces off. All of those are still considered x-intercepts. And so what we'll see is that the multiplicity is what will tell you whether the graph is going to pass through or bounce off, and then there's going to be a little bit more detail about how it will impact the shape of the graph. So the first thing I want to say is that if c is a 0 of odd multiplicity, so basically we'll see that it comes down to whether that multiplicity is an even or an odd number. So if you have a 0 of odd multiplicity, so for example, multiplicity 1, multiplicity 3, multiplicity 5, etc., then the graph of your function will pass through the x-axis at the point c0. On the other hand, if c is a 0 of even multiplicity, then the graph of f of x will bounce off. So it will touch the x-axis but not pass through. So again, in either case, it's still an x-intercept. It's still touching the x-axis, but it's fundamentally different in terms of how that will impact the shape of the graph. So we'll look at an example in just a second, but there's a little bit more specificity that we can say here. So one other fact, and I would say these first two facts are really the most important facts to know. These next two are, again, just sort of getting a little bit more detailed about the shape. So the next fact is that the larger the value of c, the more that the graph will flatten out as it passes through or bounces off. So to give you kind of an analogy for this, and this is actually, it's not so much an analogy, it actually is kind of a special case of this. So, sorry, I was just searching, you can see, microphone suddenly worse. Did not get to the bottom of it. But here, let me just show you an example that might help you kind of remember remember this idea that the bigger the multiplicity, the more the graph flattens out. So I want to compare the graphs of y is equal to x, y is equal to x cubed, and y is equal to x to the fifth, right? Those are all odd powers of x. And notice that because they're all odd powers of x, they kind of have the same shape, right? They all kind of go diagonally through the point 0, 0. But notice that the line y is equal to x, so that would be like x to the first power, right? That passes straight through. Nothing really happens at 0, it just kind of shoots straight through the graph, or through the x-axis. If we look at x cubed, well, that one starts to kind of flatten out, right, as it goes to 0. It doesn't just pass straight through, it kind of flattens out and makes its way through. And then if we look at x to the fifth, well, that flattens out even more. And if you were to do x to the seventh, that would flatten out even more, and et cetera, et cetera. So if you can kind of remember the shapes of the graphs of like y is equal to x, y is equal to x cubed, y is equal to x to the fifth, that's kind of a good way to remember what the graph is going to look like with the multiplicities of 1, 3, and 5. And don't worry, we'll see some examples in a moment if you're having trouble connecting this back to multiplicity. On the other hand, if we look at these even powers, so x squared, x to the fourth, x to the sixth, these all bounce off at 0, right? They don't go through, and that's because we have even numbers here. And then notice if you look at x squared, well, x squared just kind of momentarily touches the point 0, 0 and then bounces off. Whereas if you look at x to the fourth, that one flattens out a lot more near 0. And if you look at x to the sixth, that flattens out even more. And so again, just like if I pull up x to the fifth and x to the sixth, see how both of them have that really kind of flat shape in the middle. Okay, so let's now talk about this example. So this graph that I have sketched here, I'm debating where to write the function name, I'll write it here. So this is going to be the function f of x is equal to, and I'll just tell you, I'm going to write it in its factored form because it would be a very huge polynomial if it wasn't factored. So this is equal to x plus 1 times x to the fourth times x minus 1 squared times x minus 2 cubed. So what would be, let's write down first the zeros and their multiplicities, and then we'll kind of connect that to what we're seeing in the graph. So what are the different zeros we have? Well, we have x is equal to -1, right? If we were to set x plus 1 equal to 0, we would get x is equal to -1. And in that case, the multiplicity is just 1, right? Because the factor only appeared once. If we look at this next one, well, if x to the fourth is equal to 0, that would just tell us that x is equal to 0. And what is the multiplicity in this case? Well, it's multiplicity 4 because we have x to the fourth. Then we have x minus 1 squared is equal to 0. So that would tell us x is equal to 1. And what's the multiplicity in that case? Well, it appears twice, so it's multiplicity 2. And then finally, we have x minus 2 cubed is equal to 0. So that would mean that x is equal to 2, and that has multiplicity 3. Okay, so let's see what's going on in all these different pieces of the graph. So here's the first 0. That is at -1. And so notice that because that is multiplicity 1, the graph is just passing straight through. It's not bouncing off, and it's not flattening out at all. So now I want to compare these next two, and I'm actually going to pull this graph up on Desmos as well because it's a little hard to see, I think, on this the one that I have here. But this is the 0 with multiplicity 4, and then this is the 0 with multiplicity 2. And so notice that both of them bounce off, right? The graph doesn't pass through, it bounces off, but notice it flattens out a little bit more on the one at 0, the one with multiplicity 4. And that's because that multiplicity is a higher number. So I'm just going to go back to, or I'm going to pull up this graph because I think it's a little easier to see if we zoom in. So notice that when we're getting close to 0, the graph is really flattening out quite a bit, whereas at 1, it just kind of bounces off in a little bit of a more direct way. Then if we look at our last 0, so our last 0 is 2, that has multiplicity 3, and notice it's passing through, but it's kind of flattening out along the way. And so that would be what multiplicity 3 looks like. So that's multiplicity, how that affects the graph. I just want to quickly remind you about end behavior, and then we'll get into some other examples. So we talked about end behavior not in the last video, but in the one before that. So we basically said how there are only really 4 different shapes for polynomials. You know, they, of course, looking at this example, you know, all sorts of funny wiggly stuff happens in the middle, but the overall shape is really only going to be one of 4. And the way that you figure out which one of those 4 is by looking at the degree and the leading coefficient. So if it has an even degree, positive leading coefficient, it will look similar to f of x is equal to x squared. If it has an odd degree positive leading coefficient, it will look similar to x cubed. Even degree negative leading coefficient, it will look similar to negative x squared. And then odd degree negative leading coefficient, it will look similar to negative x cubed. Okay, so now we're going to put all of these different ideas to use, and we're going to use the zeros, the multiplicities, and the end behavior to sketch a few different graphs. So the first one we're going to do is we're going to sketch the graph of f of x is equal to negative x to the 4th minus x cubed plus 2x squared. So the first thing we want to do is identify the end behavior. So looking at this polynomial, we can see that its leading coefficient is -1. So it has a negative leading coefficient, and its degree is even. So we have a negative leading coefficient and an even degree. And so that tells us that it's going to have a general shape that looks kind of like this. Right? It's going to look kind of like negative x squared. And so to write down the end behavior in kind of the formal way that we learn to write it, we would say, as x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x also approaches negative infinity. Okay, so that's the end behavior, and we'll come back to seeing how that kind of plays out in the graph shape. The next thing we want to find is the zeros and their multiplicities. So this just goes back to what we were doing in the last video. So to find the zeros, we want to take our function and set it equal to 0 and solve for x. And we just need to make sure that we are keeping track when we're solving for x of the multiplicities. So we have negative x to the 4th minus x cubed plus 2x squared is equal to 0. So as we mentioned in our last video, sometimes it's nice to just divide everything by -1 because that will help you to factor more easily. So let's just do that to both sides. And so we would get positive x to the fourth plus x cubed minus 2x squared is equal to 0. One thing I just want to quickly mention is that, and I mentioned this when we were talking about quadratic functions, I believe, make sure that you, when you're doing something like this, when you're dividing both sides by -1 or by any number, you can only do that because you're solving an equation where it's set equal to 0, right? Because when you divide both sides by a number and the right-hand side is 0, it stays 0. However, it would not be correct to think of this as your new function or as the same function. This is not the same as f of x, right? If you were to say this is f of x, you would get the wrong end behavior, right? We saw that our original function had a negative sign, and so it had totally different end behavior. So just again, there are certain things that you can do when solving an equation, and it won't change the outcome of finding the solutions to the equation, but you wouldn't be able to just divide by -1 in the context of just working with the function. So just make sure that when you're doing things like end behavior, that you're looking at your original function and not some kind of other version of the function that you created along the way. Okay, so how do we go about solving this? Well, we want to see what we can factor out. And so we can factor out x squared from everything. So we're left with x squared plus x minus 2. And then this second quadratic, this can further be factored. So this would factor as x. So we need to get -2, so we need a -2 and a +1, or a +1 minus 2. And so in this case, it should be +2 minus 1, right? That's how we're going to get that plus x. Okay, so what are our solutions here? Well, we have x squared is equal to 0, so that will give us x is equal to 0. And the multiplicity in this case would be 2, right? Because we have x squared. This one, if we set it equal to 0, will give us x is equal to -2. And so in this case, the multiplicity is just 1 because it only appears once. This one, if we set it equal to 0, will give us x is equal to 1, and that has also a multiplicity of 1. Okay, so how do we put this all together and sketch the graph? Well, let's start by just plotting the points that we know are our x-intercepts. So we know we have 0, 0, -2, 0, and 1, 0. Sorry, my screen got a little stuck. There we go. So we have 0, 0, -2, 0, and 1, 0. So now we need to figure out basically how does the graph go between those points. And so the information that's going to tell us how the graph goes between those points comes down to a couple of things. It comes down to the end behavior and then also the multiplicity. So the end behavior, remember our graph is going to look something like this, right? So because of the general shape, we know that when we're kind of starting, let's go from left to right in sketching the graph is not going to come down like this, right? Because that wouldn't match up with the expected shape of the graph. So we know that the first part of the graph has to come in like this in order to get the correct end behavior. And then what's going to happen at 0? Well, we know that 0 is a 0 of we're at -2. My bad. This is -2, right? And so to figure out what's going to happen at -2, we have to look at the multiplicity. So the multiplicity at -2 is 1, and that means the graph is just going to pass straight through the x-axis. So I'm going to take our graph and I'm just going to make it pass straight through the x-axis. And so then it has to come back down at some point, right? If we also have an x-intercept at 0, the graph can't just keep going up. It has to come back down and hit 0. Now, how do we decide exactly how high the graph goes? How do we decide to do this versus this or this? Well, it's hard to say, and honestly, it's not till you get to calculus that you'll learn exactly how to figure that out. I'm not going to be picky about that. If I'm asking you to sketch a graph, I'm not going to care exactly how high you make it go. I'm more just looking for you to show the correct zeros and end behavior and multiplicity and all that. If you really wanted to figure out exactly how high it goes, you could plug in some numbers, right? You could plug in -1 and find the output. You could plug in -1/2. You could plug in just basically numbers in between here. But I'm not so worried about that. That's not really the point of this video. So we're just going to kind of draw whatever feels right, and then we'll look at the graph on Desmos and see how it compares. Okay, so what's supposed to happen at 0? Well, at 0, we have a multiplicity of 2, right? So that means that the graph is going to bounce off. And then while we're down here, let's just identify the fact that at 1, the graph is going to go straight through again. So it's going to bounce off at 0 and it's going to go through at 1. So I'm going to come down here, I'm going to make the graph bounce off. And then it's supposed to come back down when we hit 1, and so I'm just going to do something like that. Again, we don't know exactly how high it goes between those points, but we know that it has to come back down in order to cross through the x-axis again. So let's take a look at how we did. So the actual graph looks something like this. So I think we didn't make it go quite high enough as it should have, but like I said, I'm not too worried about that. I'm really just interested in getting the correct general shape, right? The correct zeros, multiplicities, and behavior, things like that. Okay, so let's do another example. So in this example, we're going to sketch the graph of g of x is equal to 2x to the 5th minus 8x to the 4th plus 8x cubed. So if you didn't already in the last example, I would really encourage you to pause the video and try this one yourself. So you want to find the end behavior, find the zeros and multiplicities, and then you can come back and see how you did. Okay, so first thing, let's identify the end behavior for this function. Oops. End behavior. Okay, so we want to look at the degree and the leading coefficient, and in this case we can see we have a positive leading coefficient and an odd degree. So positive leading coefficient and an odd degree. And so that tells us that the shape is going to look something like the graph of x cubed, right? It's going to be going up to the right and down to the left. And so to write that down with our kind of technical way of writing it, we would say as x approaches negative infinity, g of x approaches negative infinity. And as x approaches positive infinity, g of x approaches positive infinity. At least I think I called this graph g of x. I meant to. Yes, I did. Good. Okay, so that's our end behavior. Let's find the zeros now. So to find the zeros, we're just going to take our function and set it equal to 0. And I guess we're finding the zeros and the multiplicity. Let me write that down. Okay. So we're going to take our function and set it equal to 0. So that's 2x to the 5th minus 8x to the 4th plus 8x cubed is equal to 0. So just like in the last one, there's something that we can divide everything by that will make this easier to factor. So we can divide everything by 2 in this case. So if we divide everything by 2, we're left with x to the 5th minus 4x to the 4th plus 4x cubed is equal to 0. Okay, so what can be factored out from everything in this case? Well, we can factor out x cubed. And so we're left with x squared minus 4x plus 4. And so now we can continue to factor, and so we would get x cubed times x minus 2 times x minus 2 is equal to 0. So from x cubed equals 0, we would get that x is equal to 0. And in this case, the multiplicity is 3 because we have x to the 3rd. And then both of these would tell us that x is equal to 2. And so because it appears twice, we have multiplicity 2. Okay, so let's go up on the graph and we're just going to plot the points at 0, 0, and 2, 0. So we have 0, 0, and we have 2, 0. And then let's think about the end behavior to get this general shape. So we know that the graph is supposed to go down on the left and up on the right. And so that means that the graph should start coming from here, right? It couldn't come from above because that would give us the wrong shape. Okay, so what's supposed to happen at 0? Well, at 0, we had multiplicity 3. And so that means the graph is going to pass through, but it's going to kind of flatten out as it passes through. So I'm going to make the graph go here, and actually let me redo this because I don't think I left myself quite enough space. So it's going to come up like this. It's going to kind of go like that, right? Still doesn't look good. Let me do it one more time. Okay, that's better. And then what's going to happen? Well, we know that the graph has to come back down and hit 2, right? Like because 2 is also an x-intercept. And so what's supposed to happen at 2? Well, we know that 2 has multiplicity 2, and so that means that the graph is going to bounce off. And so the graph is going to come back, it's going to go up. We don't know exactly how much, but it's going to come back down, it's going to bounce off, and then it's going to head up, right? Because we want to make sure that our overall shape looks kind of like this. So let's see how we did. So looks pretty close, right? We can see it flattens out at 0, it goes back up, it comes back down, and it goes up again. Okay, one more example, and then we'll do one more example after that that's kind of like working backwards. So the last example we'll do, we're going to look at the graph and use the graph to write an equation, which in some ways I think is a little bit trickier. So we want to, in this case, sketch the graph of h of x is equal to negative x cubed plus 6x squared minus 7x. So just like with the other one, I would really encourage you to pause the video and try to do this one yourself. Okay, so just like we did on the last couple, we want to start by finding the end behavior. So in this case, our graph has an odd degree and a negative leading coefficient. And so that tells us that the shape is going to look kind of like negative x cubed. So it's going to be going up to the left and down to the right. So in other words, we can say as x approaches negative infinity, h of x approaches positive infinity. And as x approaches positive infinity, h of x is going to approach negative infinity. Okay, so now for the zeros. So for the zeros and their multiplicities, we want to take our function and set it equal to 0. So in this case, that's negative x cubed plus 6x squared minus 7x is equal to 0. So let's start by dividing both sides by -1 in order to give ourselves something a little easier to work with. So we end up with x cubed minus 6x squared plus 7x is equal to 0. So what can we factor from all of these? We can factor out an x. So we have x times x squared minus 6x plus 7. Okay, so how do we go from here? Well, if we try to factor x squared minus 6x plus 7, it kind of looks like it should be able to factor, but it actually doesn't factor. You can try, but you'll see that there's just no two numbers that you can come up with that will multiply to give you 7 and add up to -6. And so that tells us that we need to use the quadratic formula. So from here we can basically see that x is equal to 0 is one solution, and that has multiplicity 1. And then as we talked about in our last video, this other part would tell us that x squared minus 6x plus 7 is equal to 0. And the way that we would solve that is by using the quadratic formula. So quadratic formula tells us that x is equal to negative b, so negative 6, plus or minus the square root of b squared, so negative 6 squared, minus 4 times a, which is 1 in this case, times c, which is 7. All divided by 2a, which in this case is 2 times 1. So we would get x is equal to 6 plus or minus the square root of 36 minus 28, all divided by 2. So that is going to be 6 plus or minus the square root of 8. So similar to one that we did last time. So we saw in our last video that square root of 8 can be written as 2 times the square root of 2. So we can rewrite this as 6 plus or minus 2 times the square root of 2 over 2. And that can then be simplified because the numerator, everything is divisible by 2. So we can factor out a 2, and we're left with 3 plus or minus the square root of 2 and we're dividing everything by 2. And so we can cancel out these 2's. And so we're left with 3 plus or minus the square root of 2. And so that means that we have 2 zeros. So we have x is equal to 3 plus the square root of 2. And we also have x is equal to 3 minus the square root of 2. And I'm leaving a little space so that we can approximate these on a calculator since we'll be graphing. And then remember that from the quadratic formula, each of those zeros, it only has multiplicity 1. And again, we'll talk in a later video about exactly why that is. Okay, so if you type 3 plus the square root of 2 into a calculator, it's approximately equal to 4.4. And if you type 3 minus the square root of 2 into a calculator, it's approximately equal to 1.6. So, okay, so we have our x-intercepts. We have 0, we have 4.4, and we have 1.6. So 0, 4.4, and 1.6, something like that. And so all of our zeros have multiplicity 1. And so that means that the graph is going to pass straight through on all of them. It's not going to bounce off. It's not going to flatten out. It's just going to go straight through the x-axis. So now if we think about the end behavior, if we're going for a shape like this, then starting on the left, we need to be coming from the top in order to accomplish that shape. So I'm just going to come down like this. We're going to go straight through the axis. I'm just going to go down for a little bit. Again, we don't really know how much it goes down. I'm just kind of making something up. It's going to pass through, it's going to go up again, and then it's going to pass through again. So something like this. And again, just to reiterate, if you really wanted to get more specific, you could just plug in some numbers. Plug in 1, plug in a half, plug in 3, plug in 3.5, just plug in a few numbers between, and that would give you a better picture of exactly what's going on. So this is what the actual graph looks like. So, we're pretty close. Again, didn't get exactly right about how much it goes down and how much it goes up, but we can see that the graph passes straight through the axis at about the places that we had put on our graph. Okay, so last thing I want to do in this video is, again, like I said, kind of work backwards. So in this example, instead of graphing something, we're going to be given the graph and we want to write an equation for this polynomial. Okay, so let's call this polynomial, let's say that it's called f of x. So what are we going to do? We're basically going to do the same thing we did on the other examples, but it's just going to kind of go backwards. So we want to identify what is the end behavior. We want to identify what are the zeros and multiplicities, and then we'll use that to kind of construct the formula. I think in this case, it's going to be easier to start by finding the zeros and multiplicities. And we'll see why. Basically, the end behavior isn't going to really come in until the last step. And so let's start by finding the zeros and multiplicities. So by looking at the graph, we can see that the zeros are x is equal to 0, x is equal to 1, and x is equal to 2. Right? Those are the 3 places where the graph touches or passes through the x-axis. So what does it look like our multiplicities are? Well, for the first one, we can see the graph passes through, so it has to be an odd multiplicity, but it looks like it flattens out a little bit. So it looks like it's probably multiplicity 3. It could be multiplicity 5. Generally speaking, I would say that in this class, we're not really going to go above multiplicity 4. So for the most part, you can assume that the multiplicity is 1, 2, 3, or 4. So basically, if it looks like it's flattening out at all, it's going to be 3 or 4. If it looks like it's going straight through, it's going to be 1 or it's going to be 1. If it looks like it just bounces straight off, it'll be 2. So x is equal to 1. Well, there we can see the graph is going straight through, right? So it has to be odd multiplicity, and then it's not flattening out at all, so it's multiplicity 1. Then looking at 2, the graph bounces off. It does not flatten out as it bounces off. It just kind of hits 2 and bounces straight off, so that suggests that it's multiplicity 2. Okay, so what does this tell us? Well, now that we have these zeros, we can work backwards to figure out what the factors are. right? For each of these, it's kind of like exactly what we've been doing in the last two videos, but the other direction. So maybe let's come back to 0. Let's start with these other two because I think they're a little easier to see. So if x is equal to 1 is a 0, what would be the corresponding factor? Well, it would be x minus 1. I'll put parentheses around it. We'll see we don't actually really need them, but typically that's how we write when we're factoring. So I'll just write it like that. And then the multiplicity is 1, so this would just be to the first power, or we can just leave it as it is. Here we have x is equal to 2, and so what would be the factor that would go with? Well, that would be x minus 2. And then the multiplicity is 2, so it should be squared. All right, what about this last one? So what about x is equal to 0? What factor gives us an answer of just 0? Well, that would be x minus 0, right? Or just x. Just to give an example, anytime we had just x, actually here we have pretty much exactly what we're looking for, but if you just have x or x squared or x cubed, that's where you're going to get x is equal to 0 from. So here we have x and we have multiplicity 3, so it should be x cubed. Okay, so what is our end behavior? So let's identify that, and then we'll see how we can put all these pieces together. So based on our graph, what is the end behavior? Well, both of the ends are going down, right? So we can see that as x approaches negative infinity, f of x approaches negative infinity. And also as x approaches positive infinity, f of x approaches negative infinity. And so what does that tell us? That tells us that we must have an even degree, and we must have a negative leading coefficient. Okay, so let's try to kind of put these pieces together. So first thing I'm going to do, and I'm using red as kind of a hint that this is actually going to be wrong, but we're going to try it. So I'm just going to take these three factors and kind of put them together. So I'm going to suggest that maybe f of x is equal to x cubed times x minus 1 times x minus 2 squared. Okay, so let's check whether this would actually have an even degree and a negative leading coefficient. So one way you could do that is you could multiply this all out, right? You could multiply out x minus 1 times x minus 2 times x minus 2, and then multiply that whole thing by x cubed. But there's actually kind of a faster way. So think about what happens, like if you were going to multiply all these things together, let's try to think of what's the highest power of x that is going to emerge from this. So that would be the degree, right? So if we have an x cubed here, and then we have x to the first here, and then what's going to be the highest power of x that comes out from this thing? Well, x squared, right? And so what happens when you multiply together x cubed times x squared? You would add those exponents, right? You'd have x cubed, or actually let me just say it this way. It's going to be 3 plus 1 plus 2, which is equal to 6, right? Because again, like just think about when you're like, imagine without actually doing it, imagine you're multiplying all this out. You'd have an x cubed, you have an x, this part would be x squared minus 4x plus 4, right? That's what x minus 2 squared is. And so the very highest power of x that you could possibly get by multiplying all these three things together will come from multiplying together x cubed, x, and x squared. You can't possibly get a higher power of x than by multiplying those three things together. And so if you multiply together x cubed times x, that will be x to the 4th. Multiply that by x squared and you'll get x to the 6th. So that's how we can tell the degree is 6. Okay, now what will be the leading coefficient? So similarly, you could multiply everything out, but I would argue you can figure out what the leading coefficient would be without doing that. So it's the same idea, right? Where is that leading term going to come from? It's going to come from this highest power of x. And so basically the things I already was circling, right? X cubed times x squared. And so what is going to be the leading coefficient that comes out from that? Well, that would just be 1, right? Basically none of these factors have any kind of coefficient on them other than 1. And so when you multiply them all together, the highest power of x you're going to get will also have only a power of 1. Okay, so how does that match up with what we expected up there? So here we got an even degree, and so that is good, right? That matches up with what we wanted. But the number 1 is not a negative, right? We needed a negative leading coefficient to get the correct shape. And so this is negative, and that is wrong. And so that tells us that this whole thing is not correct. So how can we just make like a quick adjustment that would actually make this correct? Like, what could we introduce that would make this have a negative leading coefficient instead of a positive leading coefficient? Well, we could just throw a negative sign on the front, right? If we just put a negative sign out front, then if you were to multiply this all out, you would get negative x to the 6 as your highest power. And by the way, if you don't quite understand how I came up with this degree and leading coefficient, I don't want to do this in the video for the sake of time, but I would encourage you to actually just multiply this all out. It will take, 5 minutes or something, but I think once you multiply it out, you'll really understand why the degree is 6 and the leading coefficient is 1. So in this case, by similar reasoning, the degree would still be 6, which is even. So that's good. And then what would the leading coefficient be? Well, now it would actually be negative 1, because we would get negative x to the 6. And so that is a negative number, and we're good. And so this is our final answer for what the formula is for this function. So it turns out that, and I'll show you this on Desmos, this actually isn't 100% the right answer. Notice that when I made this graph, I didn't put any values on the y-axis. And the reason I did that is because I didn't want you to worry about exactly how much this graph was scaled vertically. I only wanted you to pay attention to the zeros, end behavior, multiplicities of zeros. And so the actual correct formula for this is actually going to be, we'll see, negative 3x cubed. And I just did that to make the graph kind of look a little nicer so that these were actually like stretched vertically a little bit. But if this was a test or something, I wouldn't be looking for a specific leading coefficient, except for that I would be looking for it being positive or negative, depending on the end behavior. So if we look at here, I have, so here I just wrote it, this is without the 3. So this is just negative x cubed times x minus 1 times x minus 2 squared. So notice it has all the same zeros and multiplicities and end behavior as we saw in this example, but it just is a little flatter. And so to get it to look like the one that we had, if we just take this and multiply it by 3, now it actually looks like the one that we had. But again, if this was on a test or a quiz, I wouldn't be looking for that. I just wanted to kind of, full disclosure, tell you what the actual formula was. All right, so that is it for this video. In our next video, we're going to be talking about complex zeros. So this is something that we already saw in the context of quadratic functions, and we're just going to be kind of building on that idea. So I'll see you all then.